Okay, so what I'm hoping to do is to make a bit clearer some of the sort of things I've been saying about new results I've been conjecturing about making metric spaces out of Frechet V spaces. Now, basically, I had this vague idea a few days ago, and I was very excited about it. And I recorded a video, and I recorded another video. Then I tried to write a full proof of it. It seemed to work out, but I did everything so quickly that I haven't figured out all the details of it yet. So I wanted to go through a concrete visual example, just using a very small kind of a space of very small Frechet spaces just with elements 1 and 2, and then we can consider how we can sort of change those Frechet spaces via local perturbations by changing neighbourhoods, and how this gives us a sort of notion of moves that we can make to, like, minimal moves that we can make to transform between these different Frechet spaces, and the real point is that the minimum number of such moves, adding neighbourhood, subtract neighbourhood, or replace one neighbourhood with another, the minimum number of such moves you need to convert a Frechet space S1 to a Frechet space S2, where S1 and S2 are both Frechet spaces on the same set K, that gives you a measure, a sort of metric actually, a metric, so we can call it D S1, S2, the minimum number of these perturbation moves you need to convert topological space, Frechet space S1 into Frechet space S2, and I think that basically defines a metric. So what am I showing in this picture at the top right? Okay, so in this picture in the top right, what I'm basically showing is some of the Frechet spaces, the Frechet V spaces, which are on elements 1 and 2. Okay, I'm not showing all of them, because I'm also adding the kind of constraint that each neighbourhood of a point has to contain that point. Now, you don't necessarily have to make that assumption when you're speaking about general Frechet V spaces, but we're going to make it here just to cut down the number of objects we have to deal with, so we can think about the whole collection of these things. And so basically the way I've illustrated this, you'll see that these kind of nine different spaces, and they're indicated by a point 1 and a point 2, and then there's some solid circles, and they represent neighbourhoods of point 1, and there are some dotted circles, and they represent neighbourhoods of point 2. And so in each of these systems, we basically have these points, and then point 1 is associated with a collection of neighbourhoods. There's actually only 3 options in this case. It either has to be the neighbourhood just containing point 1, or just the neighbourhood containing points 1 and 2, or its collection could be the neighbourhood containing the point 1 and the neighbourhood containing point 1 and 2. So there's these questions about what collections of neighbourhoods are going to be associated with these different points. And basically this means we end up with these 9 different possible Frechet spaces under this constraint. And you can see that we can convert between them by, for example, let's have a look at this example at the left here. In this case, the solid black circle is going around points 1 and 2. Now that's the only solid black circle, so that means there's only one neighbourhood of point 1, and that neighbourhood consists of points 1 and 2. On the other hand, there's a dotted circle around point 2. Now that dotted circle denotes that it's a neighbourhood of point 2, and that neighbourhood of point 2 just contains point 2. Now, what can we do from this particular Frechet V space? Well, one thing we can do is a kind of warp operation, which I denote by W1, warping 1. Essentially, we're replacing the type of neighbourhood, this black circle here, with a different type of neighbourhood. Before the warp, this neighbourhood of point 1 was containing points 1 and 2. After the warp, this neighbourhood of point 1 is just containing point 1. So we've just altered the sort of shape of the neighbourhood, but we haven't destroyed or created anything. Another type of sort of perturbation we can make to the topology of one of these Frechet spaces is to actually add a neighbourhood, or of course inversely subtract a neighbourhood. And you can see how this converts us from this Frechet space here to this Frechet space down here. So thinking about this kind of network, we think about the sort of minimal paths between different Frechet spaces, and I think that basically allows you to define a sort of metric space on collections of Frechet spaces. So that's the basic gist of the idea. Now, I've tried to define it a bit more rigorously in this little manuscript that I put online, although I've had absolutely no time to check it or even read it through. I just wrote it, spell checked it and put it up on the internet because I've been very frantically looking at aspects of these different things. But basically, a way I write this metric, okay, so if we want to define everything properly, we've got to define a Frechet V space S alpha. Now alpha, that sort of is a little index which is describing the nature of the neighbourhoods of in this particular space. Anyway, it's a space S alpha and it's on this set K, so its elements are from K. And we think there's a pair. Obviously it involves the set K, and it also involves this set of things which we call zeta x alpha, which are subsets of the power set of K, and we're going to have one of those for each x in K. So remember, K is just the set of elements in our space. Don't worry about alpha for now, it's an indexing thing that will become important later. P of x denotes the power set of x, that's the set of all subsets of x. So essentially, when we say that zeta of x is a subset of a power set of x, what we're meaning is that zeta of x is a collection of subsets of K. And what those subsets of K, what we call them the neighbourhoods of point x. So in other words, zeta of x is a collection of subsets of K, and we refer to those subsets as the neighbourhoods of x. And that's pretty much all there is to the definition of a Frechet space. Every point is associated with a collection of neighbourhoods, which is a load of subsets of K. Okay, so now let's talk about the alphas. What do the alphas mean? Well, say we've got one of these Frechet V spaces on K. Well, let's say we've got two of them. They're both Frechet V spaces and they both sort of live on this set K, but they can have different neighbourhood structures. So we can suppose that we have some set ik of indexes such that every Frechet space that lives on K, every Frechet V space that lives on K, it can be denoted by S alpha for some alpha belonging to this index set of K. In other words, basically the alphas just represent, like we could have an alpha or a beta or whatever, they just represent different neighbourhoods that we can have associated with things. And so basically when I write S alpha, we think of that as a Frechet space, which obviously involves K, it lives on the set K, but these collections of neighbourhoods associated with the different points, we give those the subscript alpha here to denote that they are specific, and that alpha in a sense is a kind of index which defines the type of topology upon this particular Frechet space. And so then we can talk about two different Frechet spaces that both live on the set K. We can call one S alpha and one S beta. We can think of alpha and beta as members of this index set at I of K. Anyway, the point now is we can start to think about the space of all Frechet spaces, S alpha, and then we can try and figure out a sort of if we can define a sort of metric upon this space which is sensible. Now hopefully what I was suggesting by those topological perturbation operations is equivalent to the thing I'm going to try and suggest here. Let's have a look. So basically we want to construct a mapping, so we're going to let f of k denote the set of all Frechet V spaces on the set K. We'll suppose that K is a finite set, and so we're going to have this mapping D which maps pairs of elements for it maps f of k Cartesian product f of k to the reals, and we claim that it's a metric, and we're going to give it a certain definition, then we're going to try and prove that it's a metric. So basically the idea of this D thing, before we go into the details of it, is it's essentially supposed to be a sort of distance measure, measuring the sort of topological dissimilarity between Frechet spaces S alpha and S beta, where S alpha and S beta are Frechet V spaces living on the set K. So okay then, here we come. The Frechet V metric theorem. Let f of k be the set of all Frechet V spaces on K. Let us define this mapping that actually maps it maps pairs of Frechet V spaces on the set K to non-negative reals. Now the way that this is defined is that for any pair of Frechet V spaces, S alpha and S beta living on K, we're going to define our metric to be the sum over all the elements of K of the number of subsets of K which belong to the which belong to the collection of neighbourhoods of point A under one of our Frechet spaces, but that subset does not belong to a set of neighbourhoods of point A under the other Frechet space. So in other words, what we're looking for here is no-nos. We're looking for dissimilarities because we're trying to create a distance measure here. And so one dissimilarity which we're going to be looking for is we're going to pick an element A from K, and we're going to pick a particular subset X of our space. Now if a neighbourhood's defined under the Frechet space, under the space S alpha and S beta are all identical and nicely behaved, then X is going to belong to the collection of neighbourhoods of A precisely when X belongs to the collection of neighbourhoods of B. But if there is some sort of topological dissimilarity, then we're going to have lots of examples, or some examples, where we're going to have a subset which is going to be a neighbourhood of the point A in one Frechet space sort of neighbourhood structure setup, but X won't be a neighbourhood in the other structure setup in the space S beta. And so what we're going to count up is how many times we have this sort of discrepancy where there's a particular subset which is a neighbourhood of a point in one of our two spaces, but is not a neighbourhood of a point in the other particular space. And that's essentially what d at alpha comma ds beta is. I also believe perhaps it can be defined in terms of these kind of adding and switching moves that I was showing on that picture on the right. But the essential idea is a claim that this is a metric space. Now, to try and prove this, basically I did a few different things. I don't want to go through all the details of it. Basically we need to show that it satisfies these sort of three axioms. I actually defined another function, d star, which is just 2 times d. So we show that d star is a metric, we show that d is a metric, and we want d star to, so we want these metrics to satisfy these three properties. These are our requirements for it to be a metric. Well, we want it to be non-negative, that's fine, and we want it to be symmetric. Well, we can see that our definition is symmetric from here. I mean, what this says notationally is the sum over all elements a of k of the number of x, which is a subset of k, such that either x belongs to zeta a of alpha minus a of beta, or zeta belongs to, or x belongs to zeta of beta minus zeta a of beta minus zeta a of alpha, closed set, and the count of that. So you see that that's symmetric about alpha and beta, and so we have that our metric is symmetric about alpha and beta and non-negative. So we satisfy our first sort of metric requirement. The second metric requirement is that this thing is 0 precisely when our sets are equal, which we can sort of see, because when our sets are equal, we're going to have this condition that x is going to belong to zeta a if and only if x belongs to zeta b. For any, x belongs to zeta a alpha if and only if x belongs to zeta a beta for any subset x of k and element a of k. So, you know, we have this kind of condition that our distance is only going to be 0 when s alpha is equal to s beta, and then finally you have this triangular inequality kind of notion, which I've had a go at algebraically, sort of satisfied myself of, but intuitively I find thinking about it in terms of these sort of moves, and thinking about the minimum number of sort of little neighbourhood perturbations you have to do to get from one place to another is another very good way to sort of try and convince oneself that this function d also satisfies a triangular inequality. Basically, the way I did it was to write this function down, think about the differences between them. I shall just zoom this out a bit and leave some thing on the screen, so you can watch this at your leisure. But basically, yes, what I try to do is to basically try and make it like a sort of Hamming distance, a Hamming distance sort of issue. I mean, this issue of a Hamming distance, if you have two words of the same length using the same kind of symbols, you can kind of define a sort of metric measuring the distance between those two words being the minimum number of character operations you have to make to change one word into another. Well, since these are all finite things and basically comprising of lists of neighbourhoods, essentially what you have to do is you can sort of list how many different neighbourhood changes you have to make to convert one one space into another. And that basically is just like a Hamming distance kind of problem of like word conversion. And so the sort of essence of the triangular inequality argument follows from that. There's going to be a shortest amount of sort of neighbourhood simple conversions that you have to do to convert space S alpha into space S beta, then a smallest number of symbol conversions to convert S beta to S gamma. But surely the minimal number of symbol conversions you need to do to convert S alpha to S gamma is going to be less than or equal to the shortest number of operations you need to get from alpha to beta plus the shortest number of operations you need to get to, from beta to gamma. Now, the number of operations you need to do to get from alpha to beta, that's just exactly what we define as d S alpha S beta. So that's the basic point of the thing. That's how hopefully the argument works. And what does it look like? Well, here's a fragment of what this Frechet space with two elements looks like. But as I say, there's some constraints here, so it'd be interesting to look at the larger version of this and try and get more understanding about these different sorts of moves that one can do to convert from one Frechet space to another.